All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Everyone have a good Thanksgiving? Good, good. Well, we're back for the final stretch of the semester. So Thanksgiving's always at a weird time because, you go home, you eat a lot of food, and then all of a sudden we're at the end of the semester. And so, we have final projects, final exams, everything. So it's gonna be hectic for the next few weeks, especially with this class. I know we have a big final project, but we're almost there. Okay, so over the break, I graded your guys' midterm exam. So I brought them with me today. So I'm going to give them back to you after class day. I didn't even look at the average, so I didn't see what it was. But my feeling was that it felt like the average was just about kind of the same as the first midterm. So maybe like around low 80s, high 70%. So, you guys did pretty good overall in the second exam. Okay. One thing you'll notice if you checked on Canvas already for your second exam, remember the way I'm doing the midterm exam grades, I've created two categories. One category for whichever midterm you scored higher on, so that one's going to count for 30% of your grade. And I made another category for the lower midterm, so that's going to count for 20% of your grade. So I should have already kind of swapped it. And so, if you did better on the second midterm, I kind of swapped that score into the higher category. So now your grade should kind of automatically reflect that. And so if you see any errors with that, and so if I didn't switch your score on Canvas, let me know. But that should be in there. So whichever you scored higher on between midterm one and midterm two, that one should count for a higher percentage of your grade than the other midterm. Okay. And kind of what I saw was that there was kind of a mix. So I think maybe half you guys I think scored better on the second midterm, and then half you guys scored better on the first midterm. So it seemed pretty balanced. So I think hopefully that policy was able to help you guys out a little bit if you didn't score the way you wanted to either on the first midterm or the second midterm. Okay. All right, so we'll give those out to you after the class today. In terms of what we have remaining in the course, and so I do want to finish up our set of lecture notes on constrained nonlinear programming because you are going to need it for your final project. And so I want to finish that up at the absolute latest at the end of this week. So we're going to finish up penalty terms today. And I did want to go over variable transformations. And then after that, I have one more set of lecture notes in terms of, which is kind of more like kind of the practical side of optimization. So a lot of kind of, the last set of lecture notes has a lot of kind of tips and tricks that I've personally found useful in my life kind of before this running optimization that didn't really quite fit into any other section. So and so that's kind of how I want to end this semester. And I'm hoping that we can finish that by maybe Tuesday of next week. And then next Thursday we can have just like a final project work day. And so it'll just be kind of like one big office hours throughout the class. And so if you're working on the final project and if you have questions for me, next Thursday we can have a day where I just kind of go around and just kind of help people debug issues or kind of help them formulate things for the final project, because that is our last class meeting, which is next Thursday. Okay. All right, so that's the plan moving forward. There's no more homework assignments, and so the only assignment that you have to worry about from now until the end of course is just the final project. And so I didn't want to give you guys anything more because I know the final project is going to be a lot of work. And so I want to make sure you guys have time over these next at this point, 3 weeks to finish that up. Okay. All right. Any questions about anything before we get started for today? Okay. All right. Let's go ahead and get started. And so when we left off, 2 weeks ago, actually, so before Thanksgiving and before the midterm exam, we were talking about constrained nonlinear programming. Okay. So like I mentioned, this is kind of the almost kind of the ultimate topic in this class. And so you can kind of almost think of it as everything we've been doing up to this point is kind of building up to the Q. Okay. And so, hopefully at this point, now that we've kind of reached this point in the semester, we've reached the end, we've gone over so many optimization algorithms up to this point, you can kind of see how everything you've kind of been doing has kind of built up to here. Okay. And so on the one hand, there's kind of two parts of this title that I kind of want to focus on. Okay. The first part is the constraint part. Okay. And so what this basically means is that we are working in a constrained setting here. So our objective function or our design variables are going to be subject to constraints. Okay. Okay. So we kind of ignored constraints for a while because we were learning about nonlinear programming, but now it's time to kind of bring it back. Okay. And so constraints are very common. And so a lot of times you're going to have constraints in your practical optimization problems. Your final project has a lot of constraints that you need to follow. Okay. And just to kind of refresh your memory, a constraint is basically a mathematical equation that must be satisfied by your optimal solution. Okay. And remember, we had kind of two flavors of constraints, right? Because we had two types of equations that we can use to constrain our design variables. We can either have equality constraints. Okay. And remember, equality constraints get their name because they're a mathematical formula that has an equal sign, basically. Okay. Right? And then we have inequality constraints, which are mathematical equations that have an inequality sign. Traditionally, they have a less than or equal to sign that we have to account for. Okay. Okay. So constraints was something that we mostly dealt with kind of in the first half of the class. We haven't really seen it all too much in the second half. And so when we were talking about kind of the classical methods and the linear programming, that's mostly where we saw our constraints. Okay. All right. So the second part of what we've been going over is this idea of nonlinear programming. Okay. So this is kind of everything that we focused on for the second midterm exam. Okay, so what we kind of just finished. And so nonlinear programming it's a class of optimization methods where the objective function is we basically don't assume anything about the form of the objective function. Okay. And so we can kind of sum that up by saying these are algorithms that can optimize okay. These are algorithms that can optimize an objective function of any form. Okay. This is opposed to our the techniques that we learned in the first midterm, where we either had to take derivatives or we had to rely on the fact that our objective function was linear, right? In nonlinear programming, we make no such assumptions, and so we can basically optimize any function that we want. Okay, and kind of the key tenet or kind of the key feature of all these algorithms is that we only rely on function evaluations. Okay. And so if we could do that, if we don't have to take derivatives, we don't have to assume anything about the mathematical form of the objective function, and we kind of design our algorithms with those things in mind, then that gives us our nonlinear programming algorithms. And so those are things like our Monte Carlo, our random walk, coordinate search, pattern search, and finally middle order retrieval. Okay, so those are the 5 main methods that we went over in that section. Okay. Okay, and so the last thing that we're going to talk about in this class is kind of a combination of these two ideas. And so we want to look at algorithms that again, only rely on function evaluations, but we want to do it in a way that's also going to respect our constraints as well. Okay, so if you combine these together, we get constrained NLP. Okay. So that's kind of where we are with this topic. And so before we left off, we talked about kind of a specific way to handle this. Kind of a a little bit of a cheeky way, a little bit of a kind of a I would say it's not a whole new algorithm, but it kind of incorporates the constraints into your objective function, and we call that a penalty method or penalty term methods. Okay. And so if you look at penalty term methods in the literature or even in the textbook in the class of the class, you'll see that there are a lot of variations on this idea of penalty methods. Okay? But they all kind of revolve around the same idea. And so the idea with penalty methods is that, you know, we're going to take our all of our constraints, which themselves, the constraints are mathematical equations. Okay, we're going to take our constraints and incorporate those into the objective function. So this gives us a number of advantages, right? Because what we're doing basically in our algorithms is that we're already optimizing the objective function, right? And so by incorporating the constraints into the objective function, you can kind of make the argument that we don't really have to do anything special, okay? Because typically what you do in a constrained optimization is that the constraints are kind of handled in a separate way, or in other words, they kind of change the way that we kind of form our algorithm, right? Think back to our classical methods, right? And so when we were dealing with constraints in the Tucker conditions, right, we had to kind of use a whole new approach to incorporate those constraints and to make sure that they're satisfying. Okay. With the penalty term methods, you don't have to do that. And so if you can kind of fold those constraints directly into the objective function, then you just kind of solve the objective function normally as it is, as if it were an unconstrained problem. Okay. Okay. So make no mistake, there are completely new algorithms out there that are specifically designed for constrained optimization. In fact, I actually do have one in the notes, and so it's called Sloterdijk's method of feasible directions. Okay, so those methods do exist, and so these are kind of completely new methods that are designed from the ground up to be for constrained problems, right? And so there's dozens and hundreds of more of these, but kind of for the point of where we are in the class, and I'm kind of forward thinking a little bit in terms of what's kind of the most feasible to learn in the amount of time that we have remaining, and what's kind of most feasible for you to incorporate into your project. I think kind of the most feasible way is to focus more on kind of these penalty methods, because we spent so much time talking about the nonlinear programming algorithms. And so in this way, you can still use your classical kind of coordinate search, pattern search, Monte Carlo, Nelder-Mead, and then just incorporate the constraints into a penalty term. Okay. Okay. So let me kind of show you an example of kind of what this looks like. And so I think this was kind of the example that we ended with last time. Okay. So let's say that we have a three-dimensional optimization problem. Okay. So you have f of x1, x2, x3. Okay. So this is our original objective function. And so we have x1 squared plus 4x2 squared plus x3 squared. Okay, so that's the objective function. And since this is a constrained optimization, we have to add our constraints here as well. Okay. And so the first constraints that we're going to have are these inequality constraints, which are upper and lower bound constraints. Okay. Right. So for example, what we're saying is that the value for x1 is going to be constrained between -1 and 1. Okay. The value for x2 is going to be constrained between 0 and 2. And then the value for x3 is also going to be constrained between 0 and 2. Okay. So all of these right here are inequality constraints. Okay. We also have one equality constraint here. Their equality constraint is x1 plus x2 squared minus 2. This has to equal 0. Okay. So this right here is our equality constraint. Okay. And so in these types of problems, what we want to do is we want to solve for the optimal values for x1, x2, and x3 that satisfy these constraints. Okay. So this right here is an example of a constrained optimization problem where we have an optimization problem, right? But we have to make sure that our solution follows our constraints. Okay. Okay. Let me pause here. Any questions on this so far? This is mostly just kind of a recap from last time. Okay. All right. So let's go ahead and form our objective function here. Okay. Because what we're given in this problem is our original objective function. Okay. So our original objective function is this one right here, right? But we have all these constraints as well. And so in order to solve this or to kind of properly solve this, we have to incorporate these constraints into the objective function. Okay. And so the function that we're actually going to optimize is going to be our original objective function plus all of our penalty terms. Okay. And so it looks something like this. So okay, I'm going to define a new function. So we'll call that capital F of x vector. Okay. This is going to be equal to, first thing we're going to add here is our original objective function. So x1 squared plus 4x2 squared plus x3 squared. Okay. This right here is our original objective function. Okay. Let's add in our equality constraint first, just because that one is much shorter. We only have one of those. Okay. So this is going to be plus. Actually, let me use a different color here. Plus b times x1 plus x2 squared minus 2. Okay. Remember, what we typically do for these constraints here is we usually square the entire expression so that whatever we get is going to be a positive number, okay? Because for an equality constraint, it doesn't really matter if we violate it above it or below, the constraint, it's still going to be an equal violation. So, we want to make sure, because we're minimizing the value for our objective function, that we square it, okay? Okay. I think before Thanksgiving, I think someone asked me if you can take the absolute value as well. That's also possible. But usually, but squaring it is usually a bit more standardized, because when you take the absolute value for something, you might get kinks in the objective surface, just because that's just kind of how absolute value works. But when you square something, it kind of makes the curve a little bit smoother. So mathematically, it's a little bit better to square it. That's why that's kind of typical of what you see in the literature. But technically speaking, absolute value will work too. It's just that you're kind of more likely to get stuck in a value if you do that. Okay. Okay, and so of course this equation right here in the parentheses, this is our equality constraint. Okay. Right, so if you scroll back up to the problem, that was kind of our last expression there. X1 plus x2 squared minus 2 is equal to 0. Okay. And of course, we have this b parameter that we just introduced. And so this b parameter is called our penalty parameter. Okay. We're going to talk a lot more about the penalty parameter later in the class today, but just for now, let's just assume that this is some number that you can assign. Okay. Okay. So that is the equality constraint. Okay. Now we have all of our inequality constraints. And remember, if you remember before Thanksgiving, when we have upper and lower bounds, each upper and lower bound respectively counts as one inequality constraint. Okay. So technically speaking, we have 6 inequality constraints in this problem. Okay. One for each of the upper and lower bounds for each variable. Okay. But this is where things get a little bit messy. Let me use a cool color. Use light blue. Okay. And so once again, I'm going to add a penalty parameter in front. So this A right here is another penalty parameter. Okay. And then we have all of our inequality constraints. Okay. Okay. All right, so remember, we're going to use these max functions. And so I'll review kind of what the max functions mean in a second. Let me just write them all down first. new edit. Sorry about that. Okay, so these squares are in the wrong position here, sorry. And so the square should not be on the inside here. The square should be on the outsides of the max. Sorry about that. And that's mostly just to kind of keep things consistent with the units. But you don't want to square, you actually don't want to square the inside. Otherwise, the penalty parameters are not going to work correctly. Okay. Yeah. Okay. So just kind of recap. You know, we do have to square these, just to kind of make the units consistent, but the squared is applied on the outside. Okay. Okay. So remember, you know, all of these different max functions. So let me just look at one here just to kind of show you. Okay. So this max function is going to choose. So whatever is going to be a maximum between 0 and minus x3, that's what it's going to return. Okay. Okay. All right. So let me give you a couple examples of what this would return as. Okay. And so if you look at this inequality constraint right here, this function right here, this max 0 minus x3, that is kind of the encapsulation, or that's kind of the translation of this constraint right here, right? So that constraint basically tells us that the value of x3 has to be greater than 0, okay? Whatever we obtain for it. Okay. And so let me give you a couple of examples to kind of show you what the max function does. Okay. So let's say that we're running our optimization. We're running, say, our Monte Carlo or something like that. And we are kind of sitting on a value of x3 of 1.2. Okay. Okay. So 1.2 is a value that's greater than 0, right? And so this value of x3 should be valid because it satisfies our constraint. Okay. And so if that's the case, you know, since this point right here is valid, then we do not want to add any penalty, right? We only want to penalize this point if it violates our constraint. Okay. So let's check to make sure that that's true. And so let's compute max of 0, comma, negative x3. So we have minus 1.2. Okay. So since our value of x3 is a positive 1.2, taking the negative, that's going to be negative 1.2. Okay. And so between these two numbers, between 0 and minus 1.2, which one is greater? Right? In this case, 0 is greater, right? Because 0 is not a negative number. Okay. And so based on that, this function here is going to return 0. Okay. So that's good. So that's exactly what we want, because this value of 1.2 is valid, you know, we're not going to penalize this term. We're going to keep it okay. 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 So let's look at another example. So let's say that we have a value of x3 is equal to negative, I don't know, negative 2.4. Okay. Right. This is not valid, right? So this is a value that's outside of our range. And so since this value for x3 is not valid, we want to penalize this. So we want to apply a penalty to our objective function. Okay? All right, so then we go to our max function here. So we're going to compute max of 0, comma, negative x3. Right? So since x3 is a negative 2.4, negative times negative is going to be positive. And so we have a max of 0, comma 2.4. Okay. We check and see, between 0 and 2.4, which one is higher. In this case, 2.4 is higher. Okay. And so in this case, we return 2.4. And so since we're returning a positive number, this positive number is a penalty that we're applying to the objective function. And we're applying this penalty because we're violating one of our constraints. Okay. And so you can do that for all the other inequality terms, right? And so that's essentially how the max function works. Okay. And so we use the max function because remember, we only want to apply the penalty if our constraint is being crossed or the threshold is crossed for them. Okay. And so whenever you have an inequality constraint, you need to use this max function in order to make sure that the penalty is applied properly. Okay. All right. Any questions on that? Okay. All right. And so if we look at our final objective function, and I wrote just small enough to get it to fit all on one screen. Okay. So our objective function here is a lot larger. So we have our original objective function in black. Then in purple there, we have a penalty term associated with the equality constraint. And then in blue, we have a penalty term, or I guess in this case, 6 penalty terms associated with the inequality constraint. Okay. So now that we've incorporated the constraints into the objective function like this, we can now solve this problem as if it were an unconstrained optimization. Okay. And so when I mean solve it like an unconstrained problem, what I mean is that you can use an unconstrained algorithm. So any of the 5 algorithms that we've talked about before. So Monte Carlo, random walk, coordinate search, pattern search, or Nelder. Okay. Okay. Any questions on this before we look at the code? Okay, so let's look at a code example so you can kind of see how it's implemented. Okay, and so this is constrained example 2. Okay, so this is CNLP example 2. Okay, so this is on Canvas. Okay, so this is available for you to see. And for this code, what I did was I used the Nelder-Mead optimization. So this is a method that we've seen before. Okay. Except that the only difference is that we're going to add penalty terms associated with our constraints. Okay. All right. So let's go ahead and take a look at that. Okay, so this code is available to you online. I think I need to link it to the week 15 page, right? But you can see from here, this is the file name. So we have CNLP for example 2, Nelder-Mead with penalty. Okay. Okay. So the majority of this code is going to be the same as normal Nelder-Mead, okay? Except the only difference is that we're adding our penalty term. Okay. So I'm not going to go over all of the Nelder-Mead stuff. You know, we've gone over that kind of plenty of times kind of before Thanksgiving. I'm only here going to highlight changes for you. Okay. Okay, so the biggest change, of course, is going to be the incorporation of the constraints. And so you can see here that I've basically written this code to compute the objective function in a separate function down here. Okay. Right. And so you can see here that you know, our function here is a lot more complicated than it usually is, right? And so on the one hand, I have this variable, and so this f original here, this is our original objective function at this design point, right? So we have x1, x2, x3, those are our design variables. And so our f original here is going to be x1 squared plus 4x2 squared plus x3 squared. So that's the original objective function, okay? All right, and then now we have all of our inequality constraints here. And in fact, it looks like I made the same typo here. So I need to go correct this in the code or online. Because remember, the squared here has to be applied on the outside of these functions here. Okay. I apologize for that. I'll go fix that after the class today. Okay, but you can see here that I've created these 6 G variables. We have G1, G2, G3, G4, G5, G6, right? And so each of these G variables here represent one of the inequality constraints, right? Remember, we have 2 inequality constraints per variable because we have both an upper bound and a lower bound, okay? And so we have G1 is -1 minus x1, G2 is x1 minus 1, okay? G3 is minus x2, G4 is x2 minus 2, then we have G5 is minus x3, and then G6 is x3 minus 2, okay? And so if we sum all these up with their respective max terms, we have max 0, comma G1, quantity squared, max 0, comma G2, quantity squared, all the way across, okay? That is all of the inequality constraints or all the penalty terms associated with the inequality constraints, okay? And then we have one term for the equality constraint here. So we have x1 plus x2 squared minus 2 quantity squared, okay? Then our objective function or our total objective function here is going to be the original objective function plus a times all of the inequality constraints plus b times the equality constraints, where a and b are the penalty parameters, okay? And I don't remember what I said for the penalty parameters here. Let's go check. So we said a is equal to 5 and b is equal to 5 here. So those are kind of just dummy variables. So we're going to talk about the penalty parameters a lot more today. Okay. Everything else here is just standard Nelder-Mead. So you know, everything here is basically all the same. So let's go ahead and run this code. Okay. Okay, so we can see that our optimization has converged in 33 iterations. And so if we look at the values for x best right here, okay, you can see we got these 3 variables here. And so you can see that the value for x1 is 0.869. And so that should be within our constraints here, okay? So remember, x1 is constrained between -1 and 1. And so that satisfies that constraint. Our value for x2 is 0.85. And so that is within the bounds for that. And then x3 is also within bounds, okay? So all 3 of these are within the upper and lower bounds of x1 and x2 and x3. Let's check our equality constraint here, okay? So remember, our equality constraint is x1 plus x2 squared minus 2, okay? And ideally, this should equal to 0. So let me just go ahead and plug those numbers in. So x1 here is 0.869 plus our value for x2, which is 0.8543, okay? Quantity squared, and then we're going to subtract 2 from that. Okay. All right, so when we plug those values in here, we get a value of minus 0.4, okay? So obviously this is telling us that our equality constraint isn't completely satisfied, okay? Right? And so you may be wondering kind of what's happening here, right? And so, if when we ran our optimization, we should be able to get our all of our constraints satisfied, right? But the thing with penalty terms is that, because we're not explicitly enforcing the constraints, because we're only incorporating them into the objective function, the penalty term method is what's called a soft enforcement of the constraints. Okay. And so actually, strictly speaking, you're not guaranteed to actually, satisfy all the constraints at the same time, because they're all just kind of folded into the objective function. Okay.
Is it this coincidence that the answer is pretty close to what the penalty term is from the final?
Wait, say it again.
Is it coincident that for the that is really close to the penalty?
Oh yeah, because that's what I compute here in the code. So this penalty term here, this penalty is basically a term that I compute here to tell us how far off we are for the equality constraint. Yeah. Mm-hmm.
Yeah. Okay, I wasn't sure if you did that. It was just randomly that popped in.
Oh yeah. So that penalty is strictly just for the equal. So that's basically the exact thing there. Okay. And so if you want to improve this, and so let's say that we want to improve this this value, we can increase the penalty parameter. Okay. So remember the parameter b here, right? This parameter b is the penalty parameter that's in front of our equality constraint. Okay. And so by increasing this value here, we can increase the enforcement of that constraint. Okay. So let me increase this by a factor of 5. So let me turn this to 25. And then let's rerun the optimization here and see what happens. Okay. Okay. And so with that, our optimization conversion 46 iterations. And so let's look at our optimal values here. And so our optimal value for x1 didn't change all that much. And so our optimal value for x1 is 0.8679. Our value for x2 changed a bit. And so that now is 1.0257. And our value for x3 didn't change all that much. It was 0.68679. Okay. All three of those are still within bounds. So those are still within the inequality constraints. But now when we check the value for the equality constraint, right? And so let's go ahead and compute that, even though it tells us the value right here, which is minus 0.08. But if we compute that value of 0.8679, 679 plus 1.0257, 20 squared minus 2, okay? You can see here that we get something that's much closer to 0, right? And so this is much closer than it was before. And the reason for that is because we increased the value of this penalty parameter here, okay? And so the idea is that you can play with these penalty parameters to kind of improve the enforcement of your constraints using the penalty method. Okay. And of course, we can change this even more, although there is a limit to how much you can increase this. So let's try increasing it to 50. Let's run it. Okay. And so that improved it a little bit. And so you can see here that you can keep kind of improving this and setting those values higher and higher until you get everything that you want from the result. Okay. All right. Any questions on this example here? Okay. All right. So let me go ahead and bring back the iPad. I'm going to go ahead and summarize a couple extra points from that example as well. Okay. So just to summarize. Penalty term methods only offer soft enforcement of the constraints. And so to make the method more strict in enforcing the constraints, you can increase the value of the penalty parameters A and B. Okay. And so the way that we've set it up for now, the value for A is the enforcement for the equality constraint, and the value for B is the value for the inequality constraint. Okay. All right. But that's not to say that you can change this up a little bit as well, right? And so in the case when you have a lot of different constraints, you can include more than 2 penalty parameters. Because what can happen sometimes, and you'll probably experience this with the final project, that there are going to be certain constraints that are going to be very hard to kind of satisfy in your optimal solution. And so in those cases, you can kind of individually assign them a penalty parameter to kind of make sure that the optimization satisfies that constraint. Okay. And so I think for your final project, I gave you pretty much all inequality constraints. And so, having just one penalty parameter for all of those inequality constraints probably is not going to work out that well. And so you may want to have different penalty parameters for different constraints. Okay. But I'll leave that for you guys for the final project too. Okay. Any questions on this? Yeah. Exactly, right. And you have a lot of freedom in terms of how many penalty parameters that you can include as well. And so, I will say that, for my own solution for the final project, I used 4 different penalty parameters. Just because I grouped the constraints into different categories. And so, these ones, like the stress, I grouped all the stress constraints together. I grouped all the upper and lower bounds together. I grouped the physical dimension parameters together, and then I made one more group, I don't remember. And then each of those had their own separate penalty parameters. Because one group in particular was very tricky to get to work. Yeah. Okay. All right. So the last thing I want to talk about today is a little bit more of expansion on the penalty parameters. Okay. Let me go ahead and fast forward that. So I'm jumping around in the notes a little bit. Okay. Just because we're kind of skipping the method on feasible directions, just because that's I don't think that's feasible for us to cover in the last 2 weeks of class. Okay. That was unintentional actually. But the last method I want to talk about today is kind of manipulating that penalty parameter to kind of give you improved results for your optimization. Okay. And the reason I want to talk about this today too is that this is a technique that you can use for your final project as well, right? And so, I think I've brought this up several times today, but, we've gone over basically 5, there are 5, I call them kind of basic methods that you can apply towards the final project, right? We have Monte Carlo. Well, technically, I told you can't use Monte Carlo, so that was out. So then we have random walk. We have coordinate search, pattern search, and Nelder. Okay. That's not to say that you can't combine methods together, right? And sometimes that's a very effective optimization strategy. Okay. So this is kind of very similar to a homework problem that I gave kind of right before the midterm. Right? Okay. And so even though for the final project, I tell you that you can't use Monte Carlo, that's just pure Monte Carlo. And so you can use Monte Carlo in the final project as long as you combo that together with another algorithm. Okay. And so visually it looks something like this. And so, let's say that you run algorithm 1 here. Okay. And so at the conclusion of algorithm 1, you obtain some kind of optimal result. Okay. We'll call this x1 vector. Okay. And I almost forgot. So at the input for algorithm 1, remember you have to have an initial guess, right? And so the initial guess we'll call x naught vector. Okay. Right. So all of our algorithms have to have some kind of initial guess, with the exception of Monte Carlo. Right. Monte Carlo is kind of its own kind of weird random thing, so it's kind of in its own category. Okay. And then what you can do from here is that you can take the optimal result from algorithm 1 and then use that as the initial guess for algorithm 2. Okay. Okay. And then from here, you get another optimal result. X2. Okay. And then if you're really crazy, you can add a third optimization to this, right? And get an even more improved result. And if you're even crazier, you can actually loop all this together, right? So maybe you take the optimal result from algorithm 2, feed that back into algorithm 1, and you keep kind of repeating this over and over and over again, right? And so, surprisingly, kind of almost surprisingly, kind of linking together multiple algorithms and taking the optimal result from one and using that as the initial point for another one is actually a very, very effective method. And that it's actually used by a lot of, I've used this kind of tons of times. Okay. And so I'm bringing this up, for two reasons. One reason that I think this is a very good technique that you can use for your final project. And two, it kind of feeds directly into a penalty parameter a method that we're doing over here. Okay. Okay. Because one thing that you'll see, maybe not as much as for the final project, but for a lot of kind of practice cases, when you add these penalty terms to your objective function, you're basically changing the mathematical makeup or the mathematical shape of what that objective function is. And so it's going to shift the landscape of the objective surface. And so now your valleys are going to be in different places, which it should be, right? And so it should be different to reflect the constraints, and your peaks are going to be in different places. But whenever you're kind of making kind of these big kind of mathematical changes, sometimes it might have adverse effects, and so sometimes it may not work in the way that you want. Okay. And so for the example that we just did, we increased the penalty parameter actually quite a bit. And so I actually wasn't sure what was going to happen when we increased it to 50. It turned to work out okay. I think just because that function is pretty well behaved. Okay. But normally, if you increase the penalty parameter too much, then it kind of causes your optimization to kind of do weird stuff. And so the result that you get, even though it may follow all the constraints, may not actually be an optimum of your problem, because your original objective function kind of gets lost mathematically. Okay. Okay. And so you want to be careful with raising the penalty parameter too much, because you may not be optimizing the same function. Okay. Um, and so and sometimes it's kind of hard to tell if you're in that regime or not. Okay. Okay. And so to help guard against this, and so to make it so that you kind of are always kind of you know you make sure that the penalty parameter is not dominating, you can kind of run a penalty method sequentially. Okay. Okay. And so the key here is that when you run the optimization kind of one after the other, each time you change the value of the penalty parameter. Okay. There are a few ways to do this. So there are some methods called interior methods and some methods called exterior methods. Okay. For our purposes, just because it's similar to the penalty terms that we have before, we're going to go over exterior methods. Okay. Okay. And so in exterior methods, you're going to start with a relatively small value for the penalty parameter and gradually increase it until all your constraints are met. Okay. So the reason I do this is because, depending on which method that you use, either an interior or exterior method, it's going to change the nature of the penalty terms, right? And so for us, we're using this max function, right? So we have max 0 and the constraint quantity squared, right? And so a penalty parameter like this, or a penalty form like this, it kind of lends itself more naturally to an exterior method. Okay. Okay. And so using the penalty method, so you're going to start with a relatively small value for the penalty parameter. You're probably likely going to have an infeasible solution. Okay. Okay. Right. An infeasible solution, meaning that whatever the optimum is, it's going to violate one or more of the constraints. Okay. But that's okay, because you're going to take whatever result that you get from that, rerun the optimization, but you're instead going to gradually increase the penalty parameter. So as you gradually increase it, you're going to become more and more strict with how you enforce the constraints. And then that's going to bring your result within all of the constraints. Okay. Okay. So let's go over the exterior penalty function algorithm. Okay. Because ideally, the ideal value for the penalty parameter is that it should be just large enough to make sure that all of your constraints are satisfied. Okay. It's one of those things where you don't want it to be excessively large, because if it's excessively large, then it's kind of placing undue influence on the rest of the objective function. So you want it to be just large enough to enforce those parameters, those constraints. Okay. Hence, kind of the logic behind this method. Okay. So step one. Step one is to start with your initial guess. Okay. Remember, we call our initial guess x naught vector. Okay. And we need to start with an initial value for the penalty parameter. Okay. For this example here, I'm just going to use one penalty parameter, but kind of keep in mind that you can have multiple penalty parameters as well, just like we talked about. Okay. Okay. And also for this example here, I'm only going to consider inequality constraints. So kind of similar to your project. Okay. Okay. And so how do we define what a small value is? It depends on your objective function, but you can start with the value of, say, like 0.1 or something like that. Okay. Right. But of course, if your objective function naturally computes higher numbers, then you may have to change this. Okay. Okay. Step two. So step two is to solve the unconstrained optimization of the original objective function plus your penalty term. Okay. So this is call this big F of x is equal to little f of x. Okay. So that little f of x is our original objective function, and then we have our penalty terms. Okay. And so let's say that we find the optimum of this. So we run the code for this. And we get the optimum to be xk star. Okay. Step 3. Now that we have an optimum for this, we need to check to make sure all of our constraints are satisfied. Okay. Okay. If it does, then we're good. Then we can just end. So we can just stop right here. So if it does, we can terminate the algorithm. The optimal point is xk star. Okay. If not, if our result here doesn't satisfy all the constraints, so one or more of the constraints are not satisfied, then we increase the value of the penalty parameter and then return to step 2. Okay. And so a couple things with this last step here. So usually when you're increasing the penalty parameter, you typically what's done is that you increase it by a multiple of the previous one. Okay. Let's say that a k plus 1. So that's going to be the penalty parameter. And the next step is going to be c times ak. Okay. Where ak is the previous penalty parameter. Okay. And c here is some value that's greater than 1. Okay. Because we want to make sure we want to be increasing our penalty parameter. Okay. Right. And so if you want to be aggressive, you can set c is equal to 2. And so that's going to double the penalty parameter each time. If you want it to be more gradual, you can set it to be 1.1 or 1.2. So it only increases by 10 or 20%, and so on and so forth. Okay. The other important thing for step 4 here is that when you're running the second algorithm, the third algorithm, the fourth algorithm, you want to make sure that your starting point was the optimum result from the previous step. Okay. We're going to start with xk star. Okay. So don't start with your initial starting point, or don't come up with a new starting point. You want to start with where you left off last time. Okay. Except, when you're rerunning it, your penalty parameter is different. And so it's going to find a different optimum, because it's going to enforce those constraints a bit more strongly. Okay. Okay. Any questions on this? Okay. All right. So I have a code for this, but I think we'll go over it next time. And so we're going to go over that code. Next class, we're going to go over transformation methods. So that's the last thing I want to cover in terms of constraint optimization, but I don't think that'll take too long. And then we're going to start going over practical stuff. So we're going to start wrapping up the class. Okay, so I'm going to end a little bit early today just because I have your midterm exams here, so you guys can come up and pick it up. Definitely read through the exams. I think the average was about the same as the first exam. I'll have to check. And remember that I've already kind of made the changes to your grade so that the higher midterm, whatever that was, midterm 1 or midterm 2, that's counting for 30% of your grade. Okay. And of course, if you're not here today, I'm going to bring in the exams again on Thursday, so you can pick it up then. Okay. All right. So thank you guys for coming today. I hope you guys enjoy the rest of your day, and I will see you on Thursday.
Figured out for a minute, I had the points. Oh, these are all game number 2, right? Oh, excuse me, these are all number 2?
Yes. Are you looking for your first name? Okay, and those are my offices, so you can buy off hours on.
I hated the SDA.
Okay, I think most people do.
That's just glad I was,
It was a long exam.
and then to have back to backs.
That was probably the toughest part.
At some point I'll start the project.